I'll give you a very quick outline of what I'm intending to do tonight, and the first thing I have to do is, as I'm a university lecturer, I have to give you a lecture and try and teach you something. So I'm going to talk to you a little bit about underwater sound, and particularly how it relates to what we're all more familiar with, which is sound in the air. I'll remind you of the facts associated with the loss of MH370 as far as we know them. And then what I want to talk to you about is a large number of different ways in which underwater acoustics have been involved in the search and how it's going to be involved in the next phase of the search, which is just about to take place or to start. It could be a very long process. So to start off with, of course, also being a university lecturer, I have to give you a test. So I'm not going to embarrass individual people, but I would like everybody who believes the answer to the question is A, to raise their hand, B, C, D, E, what about F? Well, we've got a pretty even spread right across the board there, apart from no one thought it was less than 1,000 metres, which is good. The correct answer is actually, it's about 4,000 metres. The ocean does get a lot deeper than that. The deepest points in the ocean are about 11,000 metres deep, 11 kilometres, but they're in quite narrow trenches associated with where tectonic plates go under one another and fancy geological type stuff like that. There's a lot of ocean around 4,000 metres to 6,000 metres, and where the current or the search for MH370 is about to take place, it varies between about 2,000 and 6,000 metres. So the average of that's about 4,000 as well. So it's deep. It's 4 kilometres straight down. Okay, next question. So here we have sunlight shining on the ocean. Some of it gets reflected off the top of the ocean, but we don't care about that. Some of it goes through. Of the sunlight that goes through, how much it makes it 100 metres down? A? 50%? No? B? 20%? Yeah, could be. C? 10%? D? E? How about F? The correct answer, again, there was a pretty wide spread apart from the first one. Everyone's allergic to the first option, I've noticed, is F. So it's not much. If you go down another 100 metres, you'll be down to, help me Igor, 10 to the minus 1% is 10 to the minus 2, so it's 10 to the minus 4. So it'd be 0.001%, something like that. Yeah, so light does not go very far down into the ocean. The ocean, the vast bulk of the ocean is dark, right? So remember that, that's important. So if you're an animal living in the ocean, unless you're living in the top little bit, having eyes is not actually terribly useful. What you need is ears. Okay, next question. Further sound has been transmitted, I should have said, by humans through the ocean and received and made sense of less than 10 kilometres, eh? Anyone? Yeah, a few people? Okay, someone's brave. They're prepared to go for the first answer. I like that. What about between 10 and 100 kilometres? Yeah, that's popular. Between 100 and 1,000 kilometres? Yeah. Between 1,000 and 10,000? What about more than 10,000? You're not allowed to answer, Sasha. Neither are you. There's a few people here who know the answers to these. The correct answer is more than 10,000 kilometres. In fact, basically, wherever you can get a line of sight without hitting land, you can get low frequency sound to travel in the ocean. And I'm going to explain a bit how that works, because it's relevant to our story. So first of all, we have to know what sound is. That's what sound is. It's a wave. Here we have these giant water particles, or air particles if you prefer, moving back and forth. But you can see the actual wave is this bit, this sort of where they're all stuck together, that's where there's a lot of air in a small volume, so that has a high pressure or a high density, and that's what's travelling. The individual air or water particles are just oscillating back and forth. So the air doesn't move, it's just the oscillation of the air particles that moves. So it's a wave. It's called a longitudinal wave because the particles are moving in the same direction as the wave is moving. It's different from, say, the wave on the surface of the water. That's going up and down. It's actually going round and round, but let's say the surface appears to go up and down, but the wave is moving horizontally. So that's called a transverse wave, whereas sound is a longitudinal wave. Sound in the water, sound in the air, same stuff. It's just a compressional wave or a longitudinal wave, and that's what it is. We can measure a few different things about it. So we can measure the density, which is how many air particles or how much mass of air or water is in a particular volume. So that's the density. So you can see where they're all crunched up together, you have a high density. Where they're all spread apart, you have a low density. We can measure the velocity of the individual particles as they go back and forth. Or we can measure the pressure, which is if you compress the air or the water, it tries to fight back, and so you've got to apply a force to compress it. So that's the pressure, the amount of force you have to exert per unit area. Turns out that that's the easiest thing to measure. So the microphones that I'm using to talk to you at the moment are pressure devices. They measure the pressure of the air on a little diaphragm that then wiggles back and forth in response to that. The sensors that we use in the ocean are called hydrophones, and they're specially designed to work well in water for a reason that I'll try and explain in a minute. If I put one of these in a plastic bag and stick it in the ocean, it doesn't work very well at all, even if the plastic bag doesn't leak. In order to understand that, I have to introduce a term that's very handy to have in the back of your mind so you can trot it out at dinner parties and things like that to impress your friends about the acoustic impedance of water is much higher than the acoustic impedance of air. It's a very useful line if you want to totally kill the conversation. I've tried it many times, it works wonderfully. So acoustic impedance is the ratio of the pressure, so that's the force that you've got to apply to compress the particles closer together in the high density parts of the wave, to the velocity that the particles move. That's all it is. Turns out that for a particular medium that has a particular density, sorry, that's a Greek letter, but it's rho, and it means, us physicists use that all the time for density. So that's the density of the material, so either air or water, and this is the speed of sound in that material. So that's what it depends on. So if you make it denser, the impedance goes up. If you increase the sound speed in the material, the impedance goes up as well. So let's have a look at how they compare. So we've got air. The stuff we're familiar with sound in has a density of about 1 kilogram per cubic metre, which is not much. Water has a density 1,000 times higher than that. Sound speed in air is about 340 metres per second. Depends on altitude and density and humidity and all sorts of complicated things, but that's a good enough number. Sound speed in water is a lot faster. It's about 4 times faster, a bit more than 4 times faster. So it's about 1,500 metres per second, or 1.5 kilometres per second that sound travels in water. Multiply those two together, boom, boom, we get 374. The units are named after Lord Rayleigh, so they're called rails. 374 rails for air, and that means 1,500,000 rails for water. So it's a lot bigger. In fact, it's 4,000 times bigger in water, the acoustic impedance. Now, it turns out that if you want to design a sensor, for example, or you want to evolve a sensor if you're an animal, if you want it to work in air, because it has a low acoustic impedance, it means that a small pressure causes a large motion of the particles. So you want something floppy for your sensor that'll move easily in response to a relatively low air pressure. In water, it's the opposite. You want something that will only move a little bit in response to a high pressure, so that it matches what happens in the water. Otherwise, it just tries to move out of the way and it doesn't respond to the sound wave. So if you go swimming, you get into the water, you've got these ears which have evolved to work in air. They work really well at the low acoustic impedance we have around us here, but they're absolutely useless in water. And consequently, we think water's really quiet. When we go for a swim down the beach, we think, oh, it's really quiet, there's nothing going on. All we can hear is our own breathing, which we're hearing through our own bone structure and stuff, and isn't coming in our ears at all. If you're really, really quiet and you're snorkeling somewhere like Point Perrin, where there's some nice reefs, you might hear this sound that sounds a little bit like frying eggs. That is actually a little shrimp that makes this really loud clicking noise called a snapping shrimp. And there are zillions of them and they make a huge racket. If you put a hydrophone in there, it's just this massive noise that you get from all these shrimp. There's a few people nodding their heads who work in underwater acoustics who will agree with that. So that's an example where we have totally the wrong impression. We think underwater it's very quiet, and I think Jacques Cousteau, who some of the older people in the audience of my vintage will remember that name, he sort of compounded the problem by writing a book called The Silent World about scuba diving, the development of scuba diving in the ocean, and he's wrong. It's not silent, it just can't hear there. Okay. Another technical, well, this is spreading loss is another good dinner party term. So you take a lump of sound, you take it from one place to another, it spreads out. So when I'm talking to you, the sound's coming out of my mouth, which is small, it's spreading out in this room. So it's got to get quieter because the same acoustic energy has to spread out into a bigger area. That's called spreading loss, and there's a magic formula that you don't need to know. The other way that sound gets quieter as it goes through the air or the water is that it's moving the particles around, and there's a certain amount of friction involved in that process. You move something with friction, it generates heat, so you lose energy out of the sound wave and you convert it to heat. That has the technical name of absorption. I've just written attenuation here to try and avoid you writing absorption, which I can't spell. So we have a little comparison table here of, it's a function of frequency. So frequency is how fast you're moving everything back and forth. How many times a second? So 10 times a second, 10 hertz, you end up with an attenuation of 0.15 dB per kilometre in air, and 0.001 dB per kilometre in water. Don't worry about what these dB per kilometres mean, but this is a lot bigger than that is. So, and as you go up in frequency, the gap narrows a bit, but at any frequency, you always have much less attenuation in air. You have much less attenuation in water than you have in air. So that's one of the reasons that we can get sound to go 10,000 kilometres in water. But we've got to use a fairly low frequency to do it. So you can see that the attenuation gets higher as the frequency goes up. So there are a few tricks. You can't always get sound to go those long distances. This is a graph that shows how the attenuation in seawater, as this thick line here, changes as the frequency changes. 10 hertz, 100 hertz, 1,000 hertz, 10,000 hertz, 100,000 hertz, 1 million hertz or a megahertz up here. The sort of stuff I'm going to talk about varies between frequencies that are way down here at a few tens of hertz, where the absorption is very low, way up to frequencies that are up here in the hundreds of kilohertz or hundreds of thousands of hertz, where the attenuation is very high, and everywhere in between. And I would point out that marine animals use that, pretty much that entire frequency range that we've got there for various purposes, communications, echo ranging, all sorts of things. So they've evolved to use this stuff. They use sound in the water, and that's why it's one reason why it's not quiet. Okay, now we get on to the oceanography part of the lecture. So, important thing to realise is that the ocean is heated from the top. The sun shines from the top, warms it up. Okay, so when you go home, I want you to get a blowtorch out of the shed. I want you to get a saucepan of water, and I want you to try and boil the saucepan of water by firing the blowtorch at the top of the saucepan. You might take a while to do that. In fact, you might take a very, very long time to do that. So you'll be able to boil the very top bit, but you won't be able to boil the bottom, and it will probably be stone cold when you finish that rather fruitless exercise. Okay, and the reason it doesn't work is because when you heat it up at the top, it gets less dense, it gets lighter, and it tries to float. So it's already at the top, so it can't go anywhere. So you don't get any mixing up of the water underneath. It just stays the way it is. And that's what the ocean's like. So it's heated at the top, not at the bottom. That's why we have our stoves and we sit our saucepan on top of the stove, okay, right? Not underneath it. So, but the ocean's not like that. So it gets colder as you go down. This is the hot part here where the sunlight's falling. You get this layer where you got a mixing process going on because you've got waves that mix the water vertically at the very top. So you get this bit here which has the obvious name of the mixed layer right at the top. Must have been a genius who thought of that one. And that's because it's mixed by the waves. How thick that is depends on how strong the wind's been blowing and for how long and things like that, and consequently how much mixing has been going on. So the temperature is more or less constant in there, and then once you get below the depth at which the waves were acting, then you get into this region where it just gets colder. And depending on whether it's summer or winter, you get warmer or cooler temperatures here, so this moves up and down a bit. So you get this bit here which changes, which is called the seasonal thermocline, but in general it just keeps getting colder until you get down to somewhere around 1,000 metres, about 1 kilometre down, and then it tends to level off pretty much, and this bit down here is called the deep isothermal layer. So yeah, all these useful words you're learning tonight. I hope you're glad you came. This bit's called the thermocline. Thermo means temperature and cline means changing, so it's changing temperature. So that's a good one to impress people with as well. Salinity we're not that interested in, it turns out, because the changes aren't very big. And this is a very notional sort of plot, and it really might not look at all like that. What we're interested in most is the sound speed, which sound speed increases as you make the water warmer, it increases as you make it more saline, and it increases as you compress it more. So as you go down in the ocean, water's heavy stuff, so the pressure goes up. Temperature's getting colder here. The temperature affects the biggest ones, so while the temperature's dropping off down here, down the main thermocline, the sound speed more or less follows the same shape. Once the temperature levels off, however, the pressure effect takes over and the sound speed increases with depth. And this turns out to be very important. This depth here at which the temperature is a minimum acts as what's called a waveguide or a duct. Sound likes to hang around at that depth. So here's a little picture that shows that. Here's a very bad picture that's supposed to look something like that previous one that shows the sound speed as a function of depth. The minimum here is at about 1,000 metres, which is pretty much where it is off Perth. Varies a bit with latitude, but not a lot. If you send a sound ray off with a bit of an upward slant from 1,000 metres, it gets into faster and faster water, or the sound speed increases as it gets into shallow water, And that causes what's called refraction. So refraction is like if you shine light into a prism or into the water, for example, it gets bent by a change in the speed of light. Same deal with sound. Wherever there's a change in the speed of a wave, it changes direction through this process called refraction. So turns out that the sound will refract downwards when it's in this region here, and then once it gets below the minimum in the sound speed, it's now getting into faster and faster water again, so it refracts back the other way. So you get this bending effect, and it ends up following, sort of going back and forth around this particular depth of around 1,000 metres. And all the other rays that you send off at other angles do the same thing. If you go steep enough, fair enough, you'll get out of the duct and you'll hit the surface or you'll hit the seabed. But sound that's caught in the duct doesn't hit the sea surface, so it doesn't get scattered by these waves that are on the sea surface. It doesn't hit the seabed, so it doesn't get absorbed into the sand or mud or whatever's down there. So you don't lose energy that way, and also it's not spreading vertically either. It's like an optical fibre in a way, except it's still spreading horizontally but not vertically. So you get you get much lower spreading loss than you had before. So the sound can travel a long way with only a very small amount of attenuation, especially if you use very low frequencies, so not much is getting converted into heat. You've got very little absorption. So it can go for a long way. So if you want to go 10,000 kilometres or more with sound, what you do is you choose a low frequency, like about 55 hertz, maybe 100 hertz, if you want to push your luck. And you put the sound source at about 1,000 metres depth, and you put your receiver at about 1,000 metres depth. And you can go right around the world. Well, you could if you didn't hit land. So that's the Marine Acoustics 101 lecture finished with. So now we're going to get onto the application of it to a particular problem, and that's trying to find MH370. Okay, so first of all we want to just it's a little while since this has been in the news, so people may need a bit of a refresher as to what actually happened. So the aircraft was lost on the night of the 7th to 8th of March. Quite a long time ago now, and we still don't know where it is. Initially, the search effort was concentrated on the planned flight path of the aircraft, naturally, which was northwards from Kuala Lumpur in the Gulf of Thailand. But somewhat suddenly, from my point of view, it was switched to the southern Indian Ocean. So thousands and thousands of kilometres away from where they were first looking. And that was based on analysis of radar data from around where the plane was when they lost contact with the aircraft, and on analysis of a handshaking signal, a radio signal between the aircraft and the satellite that occurred at about 1 hour intervals and kept happening for about 7 hours after they lost contact with the aircraft. So I'm not going to go into that in any detail. I can point you in the direction of where you can find out more information about that part of the analysis if you're interested. So basically that's where the plane should have gone. What they think it did was one of those white lines there, but they don't really know which one. This not very well drawn line here represents effectively the last communication with the satellite, which defines a circle on the Earth's surface. And so the last one defines this circle here. The other ones define these other circles. And this is all out of a report that you can get from the Australian Transport Safety Bureau's website. Effectively, it's based on, there's a satellite up here, there's a time measurement between the satellite sending a signal to the aircraft and getting a response back. From that you can work out a distance, and if you project that distance onto the Earth's surface you get a circle, which is big, really big. And then there's a lot of other analysis that's been gone into looking at Doppler shifts and other things and figuring out what is possible from the point of view of how the aircraft can fly, what speeds it can do, what altitudes it can do, and they've ended up with sort of deciding that the most likely place on that arc is down here somewhere. And this sort of, I guess, tries to sum this up. This is the circles here, this little white line. Initially, they were actually looking down here somewhere when they first went into the Southern Ocean, which is a horrible place to go looking for anything because it's very rough. It wasn't called the Roaring 40s and the Screaming 50s down there for nothing by the people who used to take sailing ships to Australia. Then it somewhat abruptly shifted up here, which is where they were searching for the pinger from the black box. And now the area they're planning on searching next is actually that orange area. So they're all along this arc. But you can see that what they think they know is where the arc is. What they're much less certain about is where along the arc it is. We thought we had made some major strides in trying to narrow that down, but unfortunately it doesn't seem to have worked out. So the first bit of the search that you've probably heard about was the black box search. So there were some detections made of underwater sound signals that were thought to have been from a pinger which is mounted on what they call the black box. There's actually two of them in the aircraft. This is a photo of a cockpit voice recorder. So this records conversations in the cockpit for the last 2 hours. The data comes, all the electrical connections are here. This bit is made to be absolutely bomb-proof, and that's where the data is stored. This little thing here is the pinger. This photograph is, unfortunately, makes it look a lot bigger than it is. The pinger is about the size of a whiteboard marker, but not as long. It's tiny. It's only about that long and about so big. So that is what they were looking for. It emits sound, it probably says here, activates when it makes contact with water. It emits sound at 37.5 kilohertz. So that was well up that absorption curve that we were looking at. Burst length, so it emits a bleep at 37.5 kilohertz. The bleep is 0.01 of a second long, and it does that once a second. And it will keep on doing that for 30 days, maybe a bit longer if you're lucky, maybe not. You can buy a version that will go for at least 60 days, but you don't spend more money than you have to on equipment like this. It's mandated that you have to have one that will go for 30 days, so the airlines never spend more money than they have to because of the cutthroat competitive nature of that industry, so they all buy the 30-day version. Which usually doesn't matter until you lose an aircraft. But you don't want to do that. You're not planning on losing aircraft, so unfortunately things don't always go according to plan. Because largely of absorption, but also because this is a very small, very low power device, it's got a small battery in it, you want it to go for 30 days. You can't emit much energy out of it, so it has a low source level. We could easily build a 37.5 kilohertz pinger that would have a lot bigger source level than these things. But not keep it going for 30 days on a little battery in a tiny little housing like that. So the detection range of these things is small. A reasonably reliable detection range would be 2 kilometres. If you're really lucky, you might get 4 kilometres out of it. But it'd have to be a good day with low noise, not much wind, no snapping shrimp, nothing sort of causing problems. These things are not designed for finding aircraft. They're designed so that if you already know where the aircraft is, you can find the black box. That's what they're for. But people in this situation are trying to use them to find an aircraft. So there's our absorption curve, and we're right up here. 7 dBs per kilometre is the absorption, which starts to kill you pretty quickly as you go out in range. This is the towed pinger locator. You probably saw photographs of it in the press. It's a pretty crude device. All it is a single hydrophone that just listens. And the only technical thing about it really is that it's designed to be towed very deep. So that the problem is you've got a detection range of 2 kilometres and you might be in 4 kilometres or maybe even 6 kilometres of water. So you can't even get to the surface. Even if you're right over the top of the thing, you can't detect it. So what you've got to do is get your hydrophone down deep so you've got some chance of detecting it. The other problem with it is all it tells you is that, yes, we've heard something, and you can record the signal, but it doesn't tell you the direction that it's come from, and you've got no idea of the distance that it's come from. So it's just a yes, I've detected something, no, I haven't. This is a map showing the green blobby bits here are where they thought they'd detected pinger signals, where the ship was. These circles are 10 kilometres in radius, which they have somewhat optimistically said was their maximum detection range, which I find rather difficult to believe. This is a more likely detection range of 3 kilometres. Right? Now the problem, you've immediately got a problem. These things are too far apart. Now there is one saving grace, and that is that there are 2 black boxes. There's nothing to say they'll be in the same place, although they are located in the same part of the aircraft. Each of them has a pinger. So there are potentially 2 pingers out there. But when you look at a map like this, and they had a lot of difficulty reacquiring the signals, if they've managed to pick it up, you know, way over here, why haven't they picked it up again when they've gone past here, for example? So there's a lot of problems even just looking at that. So after a lot of time spent out there, they started to get rather uncertain that the pinger detections were genuine, and there was some other analysis done that also made people rather uncertain. But they decided to go ahead and do a search with an autonomous underwater vehicle anyway. So this is the opposite end of the spectrum in terms of technology. The pinger detector is a pretty crude piece of device. It's just like dragging a microphone behind you. Autonomous underwater vehicle is just this amazingly high-tech piece of kit. It's a robot that you can send off by itself. They ended up doing 30 missions with it. You just program it to do what you want it to do. It goes off and does it. It's fitted with some really nice sonars that can do very nice imaging for you. And you know absolutely, if you've searched an area with this thing, whether there is anything there or not. The resolution of the sonars is down to centimetre level. So you will, if it's there, you will find it. Certainly looking for an aircraft would be, you would absolutely find something as big as a 777. There's no way you could miss it. The particular one they used, was rated to 4,000 metres, but they actually took it down to 5,000 metres, which was a bit risky, but they worked out that they could do that by pushing the sort of the engineering safety factor a bit. It has a side-scan sonar, and I'm going to tell you about side-scan sonars in a sec. This one works at 120 kilohertz, so 120,000 hertz, so that's pretty far up that attenuation curve, right up near the top. The good thing about going to high frequencies is the wavelength of the sound becomes small, so at 120 kilohertz is a bit less than a centimetre, is the wavelength of the sound, which means you can get very nice images. They searched 860 square kilometres, took them 30 missions. Each mission was about 24 hours. So it's about 30 days of actually surveying, and covered 860 square kilometres and found nothing related to the aircraft, which to those of us who had a look at the pinger data was not surprising. But it sort of needed to be done just to eliminate the possibility that they had detected something. That was the rationale anyway. This is a picture of the underwater vehicle. It's a very nice piece of kit. This is how side-scan sonars work. Now these are fairly central to our story, so I'll spend a little bit of time on it. So you've got, in this case, an autonomous underwater vehicle, but you can also have versions that you tow on a cable behind a ship. You try and get it fairly close to the seabed. And you've got this transducer, which is the thing that sends out the sound, and absolutely counterintuitively for those who aren't physicists, and absolutely intuitively for people who are, in order to get a narrow beam in the along track direction, sort of this way, you need a long transducer. And if you want a broad beam in the other direction, up and down, so you're trying to produce a beam that's like this, very narrow out to the side of the AUV, but broad up and down, and then as you go along you sort of build up a picture by your forward movement, is the way it works. So it's looking out both sides of the vehicle. I've only drawn one there. So it's long that way, small that way, and that gives you exactly the opposite as what you'd expect unless you're a physicist, which is a beam that's narrow fore and aft and wide up and down. You send a pulse of sound out. The first thing it's going to do is hit the seabed directly under it, and then as time goes on it's going to be hitting the seabed further and further out along the bottom. And what you do is you use the same transducer to measure the sound that's scattered back towards the sonar by whatever it happens to hit on the seabed. And that's how it works. And then you just build up a picture by moving the whole thing forward. So these things have been around for a long time. I don't know when it was invented, but it's sort of mid-1900s. The technology's got much better, the signal processing's got better, you can get better pictures, you can get more accurate pictures and all that sort of stuff. But the basic idea's been around for a long time. This is one I prepared earlier. This is not from the survey they did because they didn't find anything. This is much more fun. This is the Shelley convict fence in the Canning River. Anyone from Shelley? Yeah, or around about there? Yeah, okay. So if you go down to the Canning River in Shelley, you look out, you see all these posts down the middle of the river. I sail at Shelley and they're a real pain because you have to keep going around them. They were put in by convicts in order to, as part of a fence, which also has this sort of lattice work that you can't see. It's all gone down, disappeared above sea level. And the idea was to stop the river channel from silting up because the river used to be a major traffic route for moving timber, especially up and down the river on barges. Anyway, the remains of the fence are still there, and this is the remains of a dredge, which is called the Black Swan, that's wrecked next to the fence. And you can even see its little tender here, the little boat they would have used for getting to and from the shore. So this is just off Shelley. Next time you're down there in the park, if you look out, there's a couple of posts sticking out, which are probably these ones, that one, which is hard to see. That's the actual reflection from the post, but you can see the shadow much more easily. And that's often the case with side scans. So again, there's the post, which is hard to see, but the shadow is actually easy to see. So yeah, you can get great pictures with these things. And this is a really cheap one, but it's a fairly high frequency one, and we're not in 6,000 metres of water. It's 2 metres. But that's the sort of thing you get out of a side scan. They're great for detecting objects, and the shadows are extremely useful, which is one reason why it's good to tow it low down so you get big shadows. You don't get anything immediately underneath it is the only problem. Okay, I've already talked for the longest I wanted to talk, and I'm only about 2/3 of the way through. So anyway, I'll get through what I can. Okay, so that's, I guess, the pinger search, the autonomous underwater vehicle search. I want to briefly touch on some work that we did that was reported in the press. So we were looking at we weren't looking for the black box pingers, we were looking for sounds related to the aircraft actually hitting the water or parts of the wreckage imploding as it sank. That's what we were looking for. So we were looking right down the left-hand end of the absorption curve at a few hertz. So there we can have signals that can travel a huge distance. Now, we as in the Centre for Marine Science and Technology, has recorders in a number of different places for a number of different purposes. But as we run an acoustic observatory for the Australian government-funded Integrated Marine Observing System, that's just west of Rottnest Island, I think about 20 kilometres west of Rottnest Island. And we have varying numbers. We try and keep an array of 3 out there, but sometimes we don't manage that. At the time MH370 was lost, we had 2 recorders out there on the edge of the canyon. There is a big submarine canyon that cuts into the continental shelf just west of Perth that you probably didn't know about, but that's a very major feature. It's probably way bigger than the Grand Canyon, but it's underwater, so no one knows it's there. And we have them there because blue whales like to hang around the canyon, and we monitor blue whales and do stuff, fun stuff like that. But anyway, when they moved the search to the Indian Ocean, we thought, well, it's worth pulling one of those out and having a look and seeing if there's any sounds. They're recorders. You throw them in the water. There's a couple of different hydrophones here, depending on what you're after. And you go back in 6 months or whatever, you pull it up and you download the sounds that it's recorded internally onto a hard drive. So the electronics takes up about that much of the housing, the rest is all batteries. There's also hydrophones off Cape Leeuwin. So if you drive down to Augusta and go to the Cape Leeuwin Lighthouse, about halfway along that road there's a green shed on the right hand side that somebody here probably knows intimately, which is the shore station for the Comprehensive Testband Treaty Organisation hydrophone station HA01, which has 3 hydrophones 140 kilometres off Cape Leeuwin. And these hydrophones are there to monitor for clandestine nuclear explosions associated with nuclear testing. So it's part of the verification network for the Comprehensive Nuclear Testband Treaty. And Australia has paid for and maintains this station as part of its contribution to the United Nations. The data from this gets recorded in real time, so this is way more expensive than our system because it involves 140 kilometres of very tough underwater cable and lots of expensive infrastructure, but it goes by satellite to Vienna in real time and gets analysed for listening for anyone doing naughty things and letting off loud bangs in the ocean that they shouldn't be letting off. So anyway, we've used this. Sasha Gavrilov, who's down the front here, has been doing a lot of research with this data from this particular station. We get it for research purposes after it's sort of been gone through Vienna, and we use it for monitoring breakup of ice around Antarctica and for monitoring the movements of blue whales and various other things. So we were quite familiar with that data. Now, to make a long story as short as I can, the Perth Canyon logger picked up a signal that we thought was pretty interesting that was about around the time that MH370 went missing. We managed to find that same signal in the data from Cape Leeuwin. Cape Leeuwin has the advantage there's 3 hydrophones. If you look at the difference in the time the signal arrives on the 3 hydrophones, you can figure out the direction the signals come from. And you can do that very accurately, better than ±1 degree. And if you do that and project that back up, those 2 lines are sort of the bounds of where we think that sound came from, somewhere along that gap. If you compare the arrival time at Cape Leeuwin with what we measured at Rottnest, you can estimate the distance of the source, but it's not a very good estimate because these things are too close together to get a good estimate. And so you end up with this big yellow region here, which is better than nothing, but unfortunately where the satellite data puts it is down there from the satellite handshaking. So we don't think that the sound is associated with with MH370 because we really don't know what made it. There's lots of things that can make noises in the ocean. They do know what made these signals. So this has got to be considered to be more reliable data than that. If we got the range wrong and it was really back here where that crossed, which was what we actually initially thought, but unfortunately I made a typo in the program that was doing the calculation. And when we found that it was inconsistent and I recalculated it and put it up here. So you get that, unfortunately, trying to do things late at night. But even if it had been there, the timing is not what you would expect. It's about, if the source is there, it'd be about an hour too late. So, yeah. So unfortunately, fame and fortune will have to wait for another day. So that's sort of where we're at the moment. But so what I wanted to talk briefly about in the next 10 minutes that I don't have is what's going to happen next. So remember, I put this plot up before. This is the priority search area that the Australian Transport Safety Bureau, with a whole lot of people from different experts from all around the world, have come to the conclusion that this is the most likely area that the aircraft would be found in. Doesn't look very big on that map, but it's 60,000 square kilometres. This blue area is where they'd like to search if they had a lot more resources. And this grey area is where they think there is some chance the aircraft could be. Okay, so what they're going to do, starting in very soon, is search this area, and they will know when they've finished that whether the aircraft is there or not. What happens after that? We'll see. So that's the priority search area. They're currently in the middle of doing what's called a bathymetric survey, which is another good dinner party word. It means measure the water depth. So it's measuring the shape of the seabed very accurately in that 60,000 square kilometre area. That's being done by Fugro's survey, and also there's a Chinese vessel also doing that. And they've just about finished. They're using another sonar system I want to briefly mention, which is called a multi-beam sonar. And in this case, the multi-beams are mounted on the hulls of the ships, which means they can travel quite quickly, and therefore they can survey a big area in a reasonably short period of time. And they've almost finished. So the purpose of that is to do the groundwork for the underwater search. They're not expecting to be able to detect the aircraft with the hull-mounted multi-beam. It doesn't have a good enough resolution because it's so deep. The water's so deep. They can't detect objects of the size of even a 777. A multi-beam is really the good old-fashioned echo sounder, which sends out a pulse of sound straight down usually, and then times how long it takes to get a reflection back from it. It's just effectively a whole lot of those pointing in different directions across. So you're steaming along this way, and the multi-beam is looking out sideways as you go along. So a bit like the side scan, it's building a picture up as the ship moves forward. They are pretty amazing devices these days. They usually have 200 odd beams. They're very sophisticated for motion correction and all that, so that to compensate for the roll and pitch of the vessel and all sorts of stuff. But they've been around now for long enough. They're very mature technology and they're really good. So that's what they're doing at the moment. What they're about to do is a wide area search underwater of the 60,000 square kilometres. So this is actually, they're now going to go in and look for the aircraft, having now measured the shape of the seabed as accurately as they can. Fugro Survey have also got the contract to do that. And the good thing from our point of view is that it's being run out of their Perth office. Fugro Survey are a very well respected company that do a lot of work mainly for the offshore oil and gas industry. And these guys are very good at doing really precise things at sea in difficult conditions. and that's what they're going to need to do. They're going to use 2 ships. Each one will be equipped with a deep towed system. So this is a picture of one of their ships. The other one looks almost the same, so I didn't bother putting in 2. Each one of them will be fitted with one of these deep towed systems. Each of these deep towed systems will have our good friend the side scan sonar on it. It's an old technology, but it's still one of the best ways there is of finding things. And it will also have a multi-beam sonar. The purpose of the multi-beam is, they have several purposes for that, but they're going to remember that the side scan's not very good straight down. The geometry is just wrong for a side scan straight down. So you've got this sort of blind spot in the middle. So the multi-beam will be used to fill that blind spot. And if they do find the aircraft, or something that could be the aircraft, then they'll use go to the higher frequency multi-beams, go straight over the top of it with the multi-beam, and they'll be able to build up 3-dimensional pictures of what's on the seabed to centimetre or with 400 kilohertz sub-centimetre resolution. The other piece of acoustics that's on there is something that I haven't mentioned yet, which is called a ultra-short baseline acoustic position fixing system, which is better known as, for obvious reasons, a USBL. The purpose of that is you've got this thing, that's going to be 100 metres off the seabed. You could be in 6,000 metres of water, so it's going to be 5,900 metres down. You're towing it behind a ship. You're trying to go forwards as fast as you can so that you can cover the area. So you're going to need about 10 kilometres of cable in order to get it down almost 6 kilometres, and it's going to be about 4 kilometres behind the ship. So where is it? Without some way of measuring its position, you have no idea where it is. It could be, well, you might have a vague idea where it is, but not a very good idea. So the USBL system is intended to tell you exactly where it is. So this is how they're going to tow it. So they'll have a cable with a very large weight on it to try and minimise the length of cable they have to use to get down to the seabed. Here they've got a 2-ton depressor. And then the actual tow fish is on another line that comes out, and this is more or less neutrally buoyant. So the idea is that this is going to go up and down because the ship is going up and down on the surface, and what you're trying to do is minimise the motion of the platform that's towing the sonar. So this configuration means that there's less coupling of motion of that point through to the actual tow fish. So that way you get better imagery. And yeah, all you've got to do is tow this thing 100 metres above the seabed in 6,000 metres of water with about 10 to 12 kilometres of cable out. So don't get it wrong. You don't want that number to go negative. It gets very expensive. Quick word on ultra-short baseline positioning fixing systems, and then we're just about done, I think. So acoustic positioning, if you want to know where things are underwater, GPS doesn't work. Radio signals penetrate, GPS signals penetrate less than a centimetre into salt water, so that's not going to do you much good. So sound's the only thing you can use, and so there's all sorts of different acoustic positioning systems, but the one they'll be using for this is called a USBL. The way it works, you've got your cable down to your towed body. It has a thing called a responder on it. All that does is it sends out a short pulse of sound when it gets told to by an electrical signal down the cable. That sound signal travels to a hydrophone array on the boat, probably built into the bottom of the boat on Fugro's boats because they'd use these things all the time. And this has a number of hydrophones in it. Why they don't do this in the towed pinger locator, I have no idea. But instead of using one hydrophone, you use 3 or 4. You know where they are very accurately. You can measure the time of arrival difference of the signal at the different hydrophones, and from that you can determine the direction of the signal. It's done all the time in this sort of technology. by measuring the time it takes from when you send the pulse down the umbilical to when you get the acoustic signal back, providing you know the speed of sound, which you can work out if you measure the temperature and the salinity, you can work out the distance. So you've got direction from the difference of arrival times here, and you've got distance from the overall time it takes the signal to get there. So that gives you position. There's fun stuff you'd have to do in deep water to correct for refraction, so the bending of the sound as the temperature changes as you go down. But you can do all that. So you can find out where it is. And they're going to use an inertial navigation system as well on the vehicle, which measures the accelerations of the vehicle. And by combining the two, they think they can get very accurate positioning. And they should know, because that's their game. Very almost finally, mobilisation. They're in the process of getting geared up to do it all now. They're expecting to start the search by the end of September. Time to search the entire priority area, it's trivial. Each ship 1 year, 2 ships. Who's paying for it? Mainly us. So the Australian government's footing most of the bill, but there'll be some contribution from Malaysia and China, I believe, but I'm not sure how their negotiations on all that are going. It's not always plain sailing out there. So there will be downtime for weather and things like that. So wait and see, but don't hold your breath, because it could be a year before they find it. They might find it the first day, of course, which would make everybody happy except for Fugro, probably. If you're interested in finding out more about this whole process, the Australian Transport Safety Bureau have some excellent information on their website. There's a very good report giving the basis for the rationale of the search area. So I'd really recommend you look at that if you're interested. I would like to give special thanks to the Australian Transport Safety Bureau, and particularly Duncan Bosworth, who I became great mates with over the process of when we were dealing with our low frequency detections. He's in charge of the team that has been trying to determine where to look for this aircraft, and I think he's done a fantastic job. And also for Paul Kennedy at Fugro, who sent me a huge amount of information when I approached them and said, well, I'm giving this talk, how about telling us what you're actually going to do rather than so I don't have to make it up. And he sent me, it took time out from what must be an incredibly busy time for these guys getting geared up to do this in order to put together a package of way more detailed information than I've been able to have time to tell you guys. And that's an irrelevant slide, so that's the end. Thank you very much.